Hello everyone, my name is Mark Marsden and I'm here to present my CA684 project classifying musical genre from album cover aesthetics. Firstly, I'll provide some context for this area of computer vision. The concept of style and visual aesthetic has yet to be majorly addressed by the community in computer vision, but the work that has been done so far has shown some promising results. Many of the more successful work has involved repurposing tried and tested techniques from other problem areas such as object recognition to these style classification tasks. Many similar problems exist and these have yet to be tackled. One such problem area is the relationship between the album cover of a musical album and the genre that it belongs to. Musical album covers have become an essential component of modern music culture, an extension of the art form. Strong trends have developed linking distinct visual styles to different musical genres. Different color schemes, fonts, graphical design, and photographic styles can all be linked to specific genres. While there are exceptions to the rules for any given genre, this project will attempt to train a classifier to apply genre labels to an album purely based on the visual aesthetic of its cover. Firstly, a dataset will need to be generated before any experiments can be carried out. A collection of album covers sorted by genre was gathered using the iTunes Search API. This API allows the iTunes Store to be programmatically queried, returning items from specific media categories such as music albums in a JSON object. Each item contained in this JSON object has meta information such as a genre label and a URL linking to an album cover image. A Python script is written to make thousands of these such queries, as each query can only return a max of 200 items. This generates a database of over 47,000 album covers from over 200 genre labels. Now that we have a dataset of album covers, we need to decide on some features to extract and supply to a classifier. These features need to be highly discriminative and represent various visual aspects of the album cover, which may correspond to a genre label. Karyev et al. Attempted to classify paintings and photographs into respective style categories. They found higher success using object recognition techniques combined with global color distribution features. These two approaches will be combined to generate a single descriptor for our album cover classification task. Firstly, on the object recognition side of things, Fisher vector encoded CIF features have shown state-of-the-art performance for object recognition, and this feature set will be utilized for this project. This is a leading bag of visual words approach to object recognition and could prove successful for other semantic classification problems, as has been shown. Bag of visual words approach essentially summarizes the distribution of local feature primitives, in this case 128 element CIF features, to produce a highly discriminative image signature. This is implemented using INRIA's Yale library and OpenCV, both via their respective Python interfaces. The other component of our overall image descriptor will represent global color distribution. Palermo et al. Found success classifying paintings into historical periods using a joint histogram in the CIE lab color space, producing a 784 element feature vector. The CIE lab color space includes all perceivable colors and leads to a highly discriminative color descriptor. This 784 element vector is generated using OpenCV and combined with the already generated SIFT Fisher vector for a given image to produce an overall image descriptor. With our features now extracted for the entire dataset, we then need to decide on which classifier to use. Support vector machines were chosen because of the high dimensionality of the image descriptor. A large descriptor like this can lead to overfitting, where what we really want to do is learn overall trends. SVMs generate a maximum margin hyperplane between a set of data points, and when correctly tuned can successfully avoid overfitting in problems such as this. A 1-against-1 multi-class SVM approach is taken for this multi-class genre label classification problem. Before any experimentation is carried out, the dataset needs to be appropriately pre-processed. Any genre labels with less than 2,000 examples are removed as they are deemed to be not representative enough for a problem this abstract. Grayscale encoded images are also discarded as a color feature is used. This leaves a dataset of 18,500 images from 6 distinct genre labels. A training set, test set, validation set split of 50%, 25%, 25% is used for these experiments. Each genre label is split proportionally using random sampling. Using the generated test set and validation set, the SVM hyperparameters need to be optimized. A grid search approach is taken to compare different combinations of SVM kernel and C parameter. In each case, the SVM is trained using the training set and predictions are made on the validation set, with a mean average precision value calculated. The optimal mean average precision value is found using a linear kernel and a C value of 1. With this optimal hyperparameter configuration in place, performance is evaluated on the test set. Average precision, accuracy, and recall are all calculated for each class and their means are given below. A mean average precision of 0.31 is found, similar to the validation set. The confusion matrix of the test set results are shown here. For every genre apart from alternative, a successful classification is made more often than any other individual misclassification. Hip-hop and classical show the most promising results, indicating that they have a well-defined visual aesthetic. Hip-hop is often misclassified as rock and vice versa, which is an unpredicted result. Alternative has extremely poor results overall, indicating it lacks a strong visual aesthetic. Alternative is often misclassified as rock, which in itself is not unexpected given how semantically similar those two genres are. Now that we have a set of results, we need to find the contribution of each of the two individual feature sets and see how much of an improvement is made by combining them. Two more performance evaluations are run, this time using just the SIFT Fisher vector features and CAE-Lab histogram features in each case. The larger SIFT Fisher vector descriptor clearly has far greater discriminative power for this task, with only a marginal improvement made when it is combined with the CAE-Lab histogram features. In conclusion, there are some very promising results found here. For this highly abstract problem on a relatively small dataset, a mean average precision of 0.31 is found. This is a highly respectable result, especially when compared to similar style classification tasks. Karyev et al. Achieved only a 0.36 mean average precision on a photographic dataset of over 80,000 images. The question then becomes, how much better would album cover genre classification perform with a dataset of, say, 100,000 images? Global color features are clearly not discriminative enough for this task and will not be used in future. If this technique was to be combined with leading audio-based genre classification systems, this could lead to advancements in the area of content-based retrieval and automatic annotation.